the area of a hyperbolic triangle. In this video, we're going to prove a formula that allows us to calculate the area of a triangle in hyperbolic geometry. But before we can state the formula that we're going to prove, first, we need a few definitions. First, we define the angle sum of a triangle ABC to be the sum of the measures of its angles, and similarly, the angle sum of a quadrilateral is the sum of the measures of its four angles. And then we can define the defect of a triangle to be 180 degrees minus the sum of angles of a triangle. In hyperbolic geometry, the sum of the angles is always less than 180 degrees. Therefore, the defect of a triangle in hyperbolic geometry is always a positive number. Similarly, we define the defect of a quadrilateral to be 360 degrees minus the angle sum of that quadrilateral. And once again, the angle defect of a quadrilateral will always be a positive number. Before we can talk about a notion of area, we need to define some properties that an area function should have. And these are outlined in something called the neutral area postulate. These are properties that an area function should have in neutral geometry, so they'll hold in both Euclidean and hyperbolic geometry. The neutral area postulate says the following. For any polygonal region R, there has to be a number associated with R. We'll call that alpha of R, and it'll be a non-negative number called the area. The area function should have the following properties. First, given two congruent triangles, they should have the same area. And second, if a region R can be written as the union of two subregions, and those subregions do not overlap, in other words, the intersection of those regions is the empty set, then the area of the entire region should be the sum of the areas of the component regions. Next, we'll talk about a way of breaking up a region into smaller regions that respects the area function. We say that two regions, R1 and R2, are equivalent by dissection if they're sets of disjoint triangles, T1 through Tn and S1 through Sn, such that the first region can be written as the union of the triangles T1 through Tn. The second region can be written as the union of the triangles S1 through Sn, and these triangles are pairwise congruent. S1 congruent to T1, S2 congruent to T2, etc. We write this notion of equivalent by dissection using R1 triple equal sign R2. And since these regions are equivalent in terms of triangles, by the properties of the area function defined by the neutral area postulate, it implies that two regions which are equivalent by dissection must have the same area. Next, we'll state the two theorems which we're going to prove in this lecture. In hyperbolic geometry, first, if you have two triangles which have the same angle deficit, then those two triangles are equivalent by dissection. And in particular, if they have the same angle deficit, then they'll have the same area. This was a theorem proved by Bolyai. The other theorem we'll prove is that there exists a constant k such that there's a great relationship between the area of a triangle and the angle deficit of the triangle. In particular, the angle deficit is proportional to the area of the triangle. Before we start talking about area in hyperbolic geometry, a short aside, area in Euclidean geometry. To define area in this context, we typically define the area function on a rectangle ABCD to be the products of the lengths of two perpendicular sides, AB and BC. Now you can make this definition, but it does require some proof to show that it satisfies all the properties stated by the neutral area postulate. Then, to apply this definition to other figures, such as a triangle, there's a construction that creates an associated quadrilateral to a triangle. So, for example, let's say you have an acute triangle, XYZ, we perform the following construction. Find the midpoint M of the side xy, and construct the midpoint N of the side xz. Draw the line L, which passes through the points M and N, and then construct a perpendicular to L through the point Y. We'll call that J, and where J intersects L, we'll call that the point P. Similarly, we'll construct a perpendicular to the line L, which passes through the point Z. We'll call that line K, and the intersection of K and L, we'll call that point Q. Now we have a number of congruent triangles here, in particular the triangle PMY and the triangle XMR. These triangles are congruent by angle side. They both have a right angle, they have these vertical angles which are in common, and these two segments XM and MY are equal since M is the midpoint of this side. Similarly, we have some congruent triangles RNX and QNZ, again by angle side. They both have a right angle, they have these corresponding vertical angles, and this midpoint N gives us two equal sides of the triangles. And therefore, the triangle XYZ is equivalent by dissection to this rectangle PYZQ. This triangle up here corresponds to this triangle down here. This triangle up here corresponds to this triangle down here. And they both share this region in common. Since these two regions are equivalent by dissection, they have the same area. In particular, in Euclidean geometry, we have the result that the area of this triangle, XYZ, well, that's equal to the area of this rectangle, which we know is the base, YZ, times the height, PY. And the height of this rectangle can be proven to be half the height of this triangle. Therefore, we have the familiar area formula from Euclidean geometry. The area of a triangle is 1/2 the base times the height. Now, this construction is valid under the assumption that the triangle XYZ is an acute triangle. If one of the angles is obtuse, then we get a slightly different diagram, and it's a little bit more difficult to show that the triangle and the rectangle are equivalent by dissection. Depending on the size of the angles of the triangle, there are a number of additional cases that we need to discuss. Now we know that at most there can be one obtuse angle in a triangle, so without loss of generality you can assume that the angle at Z is acute. When you perform the construction on the triangle XYZ, finding the midpoints of XY and XZ, M and N, and then constructing the line through them, since the angle at Z is acute, we know that the perpendicular through Z to the line L, that point of intersection is always going to be to the right of our midpoint N. However, when we construct the perpendicular to L passing through the point Y, this point P could land in a number of different places, resulting in a number of different diagrams. Previously, when we looked at an acute triangle, P appeared to the left of M, which in turn was to the left of N. It's also possible that P could be incident with M, P could be between M and N, P could be incident with N, or M could be to the left of N and turn to the left of P. We already considered the case in which the triangle is acute. That's this first case listed here. We'll briefly consider the third and fifth case as well. The second case is just a simplified version of the first, and the fourth case is a simplified version of the third. So we'll consider cases 3 and 5, and similar to case 1, we'll show that the triangle is equivalent by dissection to the quadrilateral that we get. In this case, where the point P lies between M and N, first we take a look at the triangle XYZ. Now we could break this into 3 regions: the triangle XMN, the triangle MPY, and the quadrilateral PYZQ. Zn. Now, the triangle MPY is congruent to the triangle RMX, again by angle, angle, side. So we have this equivalence by dissection. The union of these two triangles, XRM and XMN, that gives us the larger triangle XRN, which leads us to this equivalence by dissection. And finally, this large triangle, XRN, is congruent to the triangle QNZ, again by angle, angle, side. They both have a right angle, corresponding vertical angles, and the side XN is equal to the side NZ. So we have this equivalence by dissection, but then the union of this lower quadrilateral with this triangle gives us the quadrilateral PYZQ. Next, we'll consider the fifth case, which is the most complicated of all that we have to consider. In this case, this point P lies to the right of M and N. To show the triangle is equivalent by dissection to the quadrilateral, in this case we'll first start with this quadrilateral, PYZQ. We can write this as the union of two triangles, SYZ and PSZQ. This quadrilateral, PSZQ, results from this large triangle, NQZ, subtract this triangle, NPS. That results in this equivalence by dissection. The triangle, NQZ, is congruent to the triangle, XNR. Again, that's by side, angle, side. They're both right triangles. They share this vertical angle, and XN is equivalent to NZ. That yields this equivalence by dissection. Now, the triangle XRN can be written as the union of two triangles, XMN and XRM. That leads us to this equivalence by dissection. Next, the triangle XRM is congruent to the triangle PMY. Again, by angle, angle, side, we have a right angle, vertical angles, and the side XM is equal to the side MY. These are congruent, and that leads us to this next equivalence by dissection. Now, the triangle MPY can be written as the union of two regions, the quadrilateral MNSY and the triangle NPS. And that leads us to this equivalence by dissection. But we've both added and subtracted the triangle NPS, so those two will cancel out. Now, what regions does that leave us with? It leaves us with SYZ, XMN, and this quadrilateral MNSY, and these three regions together form the triangle XYZ. Therefore, XYZ is equivalent by dissection to the quadrilateral PYZQ. Now, after doing these proofs of equivalence by dissection, we're ready to move on to talking about area in hyperbolic geometry. Now, this construction that we've seen multiple times, we start off with a triangle ABC, we find the two midpoints, M and N, construct the line through those midpoints, and then construct two perpendiculars through the vertices B and C. The intersection points are called D and E. And we have this associated quadrilateral, DBCE. Now, in Euclidean geometry, we could easily prove that the resulting figure is a rectangle, but in neutral geometry, we know that rectangles do not exist. What do we know about this quadrilateral, DBCE? Well, we do know that the angle at D and the angle at E are both right angles. Furthermore, because of congruent triangles, we know that the side DB is equal to the side AP, and we know that the side AP is equal to the side EC. So, these two opposite sides of our quadrilateral are equal. The resulting figure in neutral geometry is called a Secarial quadrilateral, or a Secarial for short. Now, secarials are sometimes rectangles. In particular, secarials are rectangles exactly when Playfair's axiom is true. So, in Euclidean geometry, we call a secarial a rectangle. However, in hyperbolic geometry, where Playfair's axiom is false, a secarial is never a rectangle. A secarial is a figure with exactly this set of properties. Before we return to our discussion of area, we'll prove some properties of secarials. First, we'll prove a property which holds in neutral geometry. So in other words, this will hold in both Euclidean and hyperbolic geometry. Typically, a secarial ABCD, the side adjacent to the right angles is called the base, the side opposite the base is called the summit, and the two angles adjacent to the summit are called the summit angles. Now it turns out in neutral geometry, we can easily prove that the summit angles of a secarial are equal. To do this, we first construct the two diagonals, AC and BD. Now we have two congruent triangles, ABC and DCB are congruent by side angle side. AB is equal to DC. The angle at B is a right angle, as is the angle at C, and they share this common side, BC. So, corresponding parts of congruent triangles are congruent, so we know the hypotenuses, the diagonals, are equal. Also, this angle, alpha 1, is equal to the angle delta 1, and this angle beta 1 is equal to the angle theta 1. Furthermore, since the angle at B is the sum of B1 and B2, that's a right angle, and the angle at C, also a right angle, is the sum of theta 1 and theta 2, since beta 1 and theta 1 are equal, it follows that beta 2 and theta 2 must also be equal. This leads us to a second pair of congruent triangles. Triangle ACD is congruent to triangle DBA, again by side angle side. We know that the diagonals are equal. We know that beta 2 and theta 2 are equal. And we know that the sides AB and DC are equal. Once again, corresponding parts of congruent triangles are congruent, so this angle in triangle ADB is equal to the angle alpha 2 in triangle DAC. Once we know those two angles are equal, we know that the angle at A, alpha 1 plus alpha 2, is equal to the angle at D, delta 1 plus delta 2. In other words, the summit angles are equal, which was what we wanted to prove. Next, we'll prove a theorem about secarials which holds only in hyperbolic geometry. We call it the summit congruence theorem for hyperbolic secarials. So let's say we're given two secarials whose summit angles are equal, so the angles at A, D, E, and H are all the same, and the summit sides are equal, so AD is equal to EH. Then, in hyperbolic geometry, it follows that these two secarials are congruent. In other words, the side AB is equal to the side EF, which implies that all these sides, AB, CD, EF, and GH, must be equal. And furthermore, the side BC is equal to the side FG. To prove this, we use proof by contradiction. Let's assume to the contrary that two parts, AB and EF, are not equal. If AB and EF were equal, then you could pretty quickly also prove that BC and FG are also equal. So let's instead assume that AB and EF are different. One of them must be smaller than the other, so without loss of generality, we'll assume that AB is smaller than EF. So here's our secarials, ABCD and EFGH. AB is the smaller side, so we'll extend AB to a point F' so that AF' has the same length as EF. Similarly, let's extend the side DC to a point G' so that DG' has the same length as HG. Next, let's draw some diagonals, the diagonal from F prime to D and the diagonal from F to H. Now we have two congruent triangles. F prime AD is congruent to FEH by side angle side. F prime A is equal to FE by construction. By hypothesis, the angle at A is equal to the angle at E, and also by hypothesis, the summit side AD is equal to the summit side EH. Then, since corresponding parts are congruent, we know that F prime D is equal to FH, and also these angles, F prime D G prime and FHG, are also equal. This in turn leads us to a second pair of congruent triangles, the triangle F prime D G prime and FHG are also congruent, once again by side angle side. These diagonals are congruent, the angles are congruent, and again by construction, DG prime has the same length as HG. Therefore it follows that the angle at G prime must be equal to the angle at G. In other words, this is a right angle. And similarly, the length of F prime G prime is equal to the length FG. We can go through a similar process, construct the diagonal from E to G and the diagonal from A to G prime, and we could prove that the angle at F prime is also a right angle. And here's where something goes wrong. This would imply that B F prime G prime C is a quadrilateral, but all the angles are right angles. Now, by hypothesis, we're working in the context of hyperbolic geometry, and we know that in hyperbolic geometry, no rectangles exist. That means our initial assumption that the lengths of A, B, and EF were unequal must be incorrect. The lengths A, B, and EF are in fact equal. From this, it's straightforward to prove that BC and FG also have equal lengths, so the two secarials are in fact congruent, which was what we wanted to show. Now that we've proven some results about secarials, we're ready to prove a theorem about the relationship between a triangle and its associated quadrilateral. It turns out that no matter what kind of a triangle you're working with, the associated quadrilateral is in fact a secarial, that the angle deficit of the triangle is equal to the angle deficit of the secarial, and the triangle is equivalent by dissection to the secarial. So they'll also have the same area. Now, as we mentioned before, the construction, starting out with a triangle ABC, we construct the midpoint of AB, the midpoint of AC, and join these points by a line L. And then we construct two perpendiculars to the line L, one running through the vertex B of the triangle, and one running through the vertex C of the triangle. And these new 2 points of intersection, we call them D and E. Now, again, without loss of generality, you can assume that one of the angles of your triangle is acute. We'll just assume that's the angle C, and so in all our configurations, we'll have N located between M and E. The position of D could fall into one of 5 cases. Either D is to the left of M, D is incident with M, D is between M and N, D is incident with N, or D is to the right of M and N. And so we'll look at these 5 cases and show that all of these statements are true in each of these cases. We'll see that all the proofs are relatively similar. They each involve a lot of congruent triangles. In our first case, we start with our triangle ABC, and we've marked the angles of ABC. A, we've marked that as a sum of 2 angles, alpha 1 and alpha 2. The angle with vertex B, we've marked that as beta. The angle with vertex C, we've marked that as theta. And again, we go through our construction. D is to the left of M and N. And as before, we have congruent triangles. DMB is congruent to PMA by angle side. That means this angle, marked as alpha 1, is congruent to this angle, which we can then mark as alpha 1. And the side DB is congruent to the side AP, so we mark them as equal. Then we have the triangles PNA and ENC again congruent by angle, angle, side. So the angle marked here as alpha 2 is congruent to this angle down here, which we can mark as alpha 2, and the side AP is equal to the side EC. So the resulting diagram is a secarial because we have two right angles and we have two equal sides. Furthermore, to show that the angle deficits are the same, the angle deficit of triangle ABC is 180 minus the sum, alpha 1 plus alpha 2 plus beta plus theta, and the angle deficit of the secarial DBCE is 360 minus the sum of these angles. Those angles sum to 180, plus the rest of the angles in the quadrilateral. That's alpha 1 plus beta plus theta plus alpha 2. And these two are equal. Case 2 is like a simplified version of case 1. Here, D and M are incident, and so the diagram looks like this. Here we only have one pair of congruent triangles. Triangle DNA is congruent to triangle ENC by angle, angle, side. So the angle at A, which is just alpha, is equal to this angle, which is alpha. Since M is the midpoint of AB, we know that BM is equal to MA, but MA corresponds to the part EC. So again, we have a secarial. These two sides are equal. We have two right angles. The angle deficit of triangle ABC is 180 minus the sum, alpha plus beta plus theta. And the angle deficit of the secarial is the same, 360 minus 180 degrees from these two right angles, and the sum of beta, theta, and alpha. So again, these two are equal. And the figures are equivalent by dissection. You just have to move this triangle ADN down into this position of ENC. Here's the third case, in which the point D is between the points M and N. Again, we've seen this case previously. We know that the triangle is equivalent by dissection to the quadrilateral. We're really interested in the fact that this is a secarial, and that the angle deficits are the same. So again, with our congruent triangles, we notice that this angle, beta 1, is equal to this angle, beta 1. The triangle ANP is congruent to the triangle ENC by angle, angle, side. And this angle, PAN, is alpha plus beta 1. That angle is congruent to NCE, so we mark that as alpha plus beta 1. The angle deficit of the triangle ABC is alpha plus beta 1 plus beta 2 plus theta. And the angle deficit of the secarial is 360 minus 180 degrees from the right angles, minus beta 2 plus theta plus alpha plus beta 1. Once again, they're equal. In case 4, our point D is incident with a point N, and this case is basically like case 3. We have the same congruences of triangles. PMA is congruent to NMB by angle, angle, side. These angles, marked as beta 1, match up. Then the triangle PNA is congruent to the triangle ENC. And so this angle, which is alpha plus beta 1, again is equal to this angle, which we can mark as alpha plus beta 1. And again, the angle deficit of triangle ABC is 180 minus alpha plus beta 1 plus beta 2 plus theta. And the angle of the secarial is the same, 360 minus the sum, 180 plus beta 2 plus theta plus alpha plus beta 1. And finally, the last case, the most complicated case. Again, we've seen this before. We've seen that the triangle is equivalent by dissection to the quadrilateral to show that the angle deficits are the same. Again, we've got our congruent triangles. Triangle PMA is congruent to triangle DMB by angle, angle, side. And so this angle beta 1 matches this angle beta 1. And triangle PNA is again congruent to triangle ENC. So this angle, alpha plus beta 1, corresponds to this angle, which we can then mark as alpha plus beta 1. We calculate the angle deficit of the triangle, and once again that matches the angle deficit of the secarial. And that completes the proof of this result, that given a triangle, the associated quadrilateral is in fact a secarial. It has the same angle deficit as the triangle, and the triangle and the quadrilateral are equivalent by dissection, thus have the same area. With these results in hand, we can now prove Bolyai's theorem. It's a very exciting theorem. It says that in hyperbolic geometry, if two triangles have the same angle deficit, then those two triangles are equivalent by dissection, which means they have the same area. It's a fascinating result. There's nothing like it in Euclidean geometry. The measures of the angles tell us nothing about the area of a triangle, but in hyperbolic geometry, these two concepts are definitely related. So let's begin the proof. First, we start with two triangles, ABC and XYZ, and we'll assume that they have the same angle deficit. Without loss of generality, we'll assume that the triangles are chosen so that the side AB is less than or equal to the length of the side XY. We'll construct the midpoint of AB, we'll call it M. The midpoint of AC, we'll call that N. Now because AB is less than XY, the segment BM is less than or equal to half the segment XY. However, we could also find a point P on this segment far enough away from M such that the length of B to another point P is greater than half the length of XY. So, by the intermediate value theorem, there must be some point Q on this line L such that the length of BQ is exactly equal to half the length of XY. So we'll mark that point, and then draw the segment BQ and extend it to a point R so that BQ and QR are equal in length. Choosing R in this way makes Q the midpoint of the segment BR. So after we construct this point R, we can also connect the point R to the point C, and we have two triangles, ABC and RBC. These two triangles share the same base, BC. Next, we want to prove that these two triangles, in fact, have the same associated secarial. We'll start by constructing the secarial associated to the triangle ABC. We have the midpoints M and N, we construct a line L which goes through M and N, and we construct our perpendiculars. One through the point B and one through the point C. Mark the new 2 points as D and E. Our associated secarial is DBCE. Next, the segment RC intersects the line L in some point. Let's mark that point of intersection as S. Now, we already know this midpoint Q lies on the line L. If S is in fact the midpoint of RC, then constructing the secarial to RBC, that would give us the same line L, and it would follow that RBC has the same secarial. Because if Q and S are both midpoints and we have the same line L, we're constructing perpendiculars from the same base points B and C. So to show that S is in fact the midpoint, first let's drop a perpendicular from R to the line L. We'll call that point of intersection P. Now moving to this side of the diagram, we know that the triangle DQB is congruent to the triangle PQR by angle side. They both have a right angle, corresponding vertical angles, and BQ is equal to QR by construction. This also implies that the side DB is equal to the side RP, because corresponding parts of congruent triangles are congruent. But we also know that EC is equal to DB, because DBCE is a secarial. Then once again, by angle side, we have two congruent triangles. SPR and SEC are congruent. They have the vertical angles equal, the right angles, and RP is equal to EC. So once again, corresponding parts are congruent. That means RS is equal to SC. So S is in fact the midpoint of the side RC. That means constructing the secarial of RBC will result in the same line L as the secarial of ABC. So these two triangles have the same associated secarial. So to summarize this, triangle ABC has the secarial DBCE. The angle deficits of these two are the same, and the triangle and the secarial are equivalent by dissection. We just showed that RBC has the same associated secarial, so again, they have the same angle deficits, and they're equivalent by dissection. So, by transitivity, these two triangles, ABC and RBC, have the same angle deficit, and they too are equivalent by dissection. Now, why did we go through all this? Well, we want to somehow relate the triangle ABC to the triangle XYZ. All we knew initially is that they had the same angle deficit. So RBC is like an intermediate triangle. It has the same angle deficit as XYZ, but it also has something else in common. Since BQ was equal to half of XY, BR, the side of the triangle, is equal to XY. So these two triangles have a side in common. So next, we'll construct the secarials for these two triangles, but to make the proof more comprehensible, we'll reorient the triangles so the matching sides are both at the bottom of our diagram. So we'll construct the secarials as shown, and then we have a series of equalities. The angle deficit of this secarial, GRBH, is equal to the angle deficit of this triangle, CRB. But the angle deficit of this triangle is equal to the angle deficit of our other triangle, XYZ. And this, in turn, is equal to the angle deficit of its associated secarial, VXYW. So these two secarials have the same angle deficits. This, in turn, implies that the sum of the summit angles on each is equal. It's a little bit odd because here the base is actually at the top of our diagram, GH and VW. So the summit angles are down here at R and B and X and Y. But since the angle deficits are equal and the summit angles within a secarial are equal, it implies that, well, everything's equal. So we have equal summit angles between the two secarials, and also we have equal summit sides. RB is equal to XY. Well, we proved earlier that that's enough to conclude in hyperbolic geometry that these two secarials are in fact congruent. Two polygons which are congruent are clearly equivalent by dissection. So therefore we have the following string of equivalences. The original triangle ABC, through the help of some secarials, we showed that was equivalent to the triangle RBC, which in turn is equivalent to its secarial, GRBH, which we just explained was equivalent to this other secarial, VXYW, which in turn is equivalent to its associated triangle, XYZ. By transitivity, these two triangles, ABC and XYZ, are equivalent by dissection, but if they're equivalent by dissection, that means that they have the same areas. And that completes the proof of this theorem. Our initial assumption was just that these two hyperbolic triangles had the same angle deficit, and from this we were able to conclude that they have the same area. Now we actually have one more theorem to talk about. We've shown that two triangles with the same angle deficit have the same area. And now we're going to use this to prove the fundamental relationship between area and deficit. That there exists some constant number k such that for any triangle, the area of that triangle is proportional to the deficit of that triangle. We break this proof into two steps. The first step, we're going to show that for any two triangles, a triangle ABC and a triangle XYZ, that the ratio of area to deficit is constant. So the area of ABC divided by the deficit of ABC is equal to the area of XYZ divided by the deficit of XYZ. We'll break this down into a proof by cases. For case 1, let's consider the case where the angle deficits of these two given triangles are the same. Well, we actually just proved that if the deficits of the triangles are the same, then the area of the triangles are the same. In which case, these two fractions must be equal, since the numerators are equal and the denominators are equal. For the second case, let's assume that the ratio of the angle deficit of triangle ABC to the angle deficit of triangle XYZ, let's assume that that ratio is a rational number, A over B. And we'll assume that A is less than B. If A was equal to B, well, that falls in case 1. Now here's what we'll do. We'll take the triangle XYZ, and what we're going to do is choose a sequence of points on the side YZ. We're going to choose a total of B plus 1 points, so P0 is equal to Y, and P1, P2, to PA. Since A is less than B, this occurs before point PB, which will be equal to the right endpoint, Z. We'll choose these points so that the angle deficits of each one of these triangles from X to PN plus 1, so that the angle deficit of each one of these triangles is 1 over B times the angle deficit of the whole triangle, XYZ. In other words, we're subdividing the triangle XYZ into a total of B smaller triangles, each of which has the same angle deficit. We know we can do this because angle deficit is additive. Furthermore, since each one of these small triangles has the same angle deficit, it follows that each one of the triangles has the same area. Now, the angle deficit of the triangle ABC, we look at this equation up here, we multiply both sides by the angle deficit of XYZ, get this expression right here, but 1 over B times the angle deficit of XYZ, that's equal to the angle deficit of each one of these little triangles. So for instance, when n equals 0, we could use that one. A times the angle deficit of this first small triangle. Well, if we have A times the deficit of one triangle, since each one of these triangles has the same deficit, this will be equal to the angle deficit of A of these triangles altogether. In other words, if we consider the first A of these triangles, we take their union, we'll get the triangle from X to P0 to PA. Now the area of one of these triangles, let's call that R. So R is the area of triangle X, P0, P1. Then the area of the entire triangle, XYZ, or this other notation, triangle X, P0, PB, that consists of B copies of this small triangle, X, P0, P1, so the area of the entire triangle is B times R. Similarly, to find the area of triangle ABC, well, triangle ABC has the same deficit as triangle X, P0, PA, so the area of ABC is equal to the area of X, P0, PA, and this triangle is made up of a total of A smaller triangles, each of which has area R. So there's the area of triangle ABC. And then if you look at this ratio of areas, you get A times R divided by B times R. Well, the R's cancel out, leaving you with A over B, which was the ratio of the angle deficits of the triangles. Then by some algebra, we have the ratio of the areas equal to the ratio of the deficits. We can turn that into this equation right here. And that completes the proof of case 2. Finally, case 3, what if the ratios of the angle deficits of these triangles is not a rational number? What if it was an irrational number? When this ratio is irrational, we'll just take a sequence of rational numbers which converge to this ratio. This equality is true for all rational numbers, so in the limit it'll stay true when the quotient of angle deficits is irrational. And now we finish off the proof. Step 1 was really the heavy lifting. In step 2, we start off by choosing any triangle, any hyperbolic triangle ABC. Then consider the area of triangle ABC divided by the angle deficit of triangle ABC. That ratio, we'll say that's equal to some number k. And then for any other triangle XYZ, we know that this ratio of area to angle deficit must always be equal to the same number k. And so, multiply both sides by the angle deficit, and you'll get the area of triangle XYZ is equal to k times the angle deficit of triangle XYZ. And that's what we wanted to prove. And this really is an astonishing result if you think about it. This says that any area function we define in hyperbolic geometry, it must take the area of a triangle XYZ, it must be equal to some constant multiple of the angle deficit of that triangle. So any area function has to have this form. Typically, we'll just choose the constant k to be 1 when we define our area function. And so, in hyperbolic geometry, the area of a triangle is equal to its angle deficit.